So we got chapter review for chapter 5 here, number 10. Tells us that this is the region under one arch of the sine x curve is revolved around the x-axis to form a solid. And this is use the method that we looked at in 5.1, example 3. We did that with a half circle, if you remember. Set up a Riemann sum that approximates the volume of the solid. So ultimately, if we were just to find the area and we wanted to set up a Riemann sum, we would just make rectangles here and we would figure out what the area of each rectangle is and so on. But if we make this a three-dimensional shape, if we revolve this, then the rectangles that we create here, whether they're from LRAM or RRAM, okay, they become, instead of rectangles, they're three-dimensional, which ultimately are cylinders. So each of those cylinders then we know has the volume pi r squared h.
So they're kind of like coins.
Yeah, I mean, I guess it'd be looking like a nickel from the side view, if you will. All right. So ultimately, again, this would be in a way to approximate it as long as we could write a formula here for each of those cylinders, which we certainly can, because every one's the same shape. They're all cylinders. They all have different radii, okay, but ultimately it's the same shape. So that means we'll work with that equation pi r squared h. Okay. So bottom line is we're going. We just want to set up a Riemann sum. It doesn't really give us any more specific than that. It doesn't say to use a certain amount of subintervals or whatever. So just for argument's sake, we know that this is pi right here. This is pi over 2. So let's say we make 4 subintervals. So we'll do pi over 4, 3 pi over 4, so on. And so ultimately, again, whether we use LRAM or RRAM or MRAM, that's up to us. It just says use the Riemann sum. So again, it's up to you on which one you use. Let's do LRAM here. So if we do LRAM, okay, the first rectangle, and remember I just drew some generic rectangle in there in the middle, but ultimately in LRAM I'm going to draw a rectangle, and it's going to have no area whatsoever because it's got no height. The height's measured from the left-hand point. If I do the LRAM one from here, I'm going to have that one, and then I'm going to have up to here, and then up to here. And so I'm ultimately going to have those three. So I'm redrawing my picture then and making it three-dimensional. My bad art. It'll look something like that. Okay. So ultimately, again, instead of rectangles, those are side views, if you will, of the three-dimensional shape, which will be a cylinder for us. And so again, what we want to do here is come up with an area formula, which we already have, and see if we can fill in the blanks. So let's look at again, from the first subinterval here, 0 to pi over 2, there is no rectangle, so therefore there is no cylinder, so that's 0. With the second one, our radius of our cylinder, remember, is the height here at pi over 4. Well, sine of pi over 4 then is radical 2 over 2. And then the thickness of each of these is going to be pi over 4, because ultimately we're going from 0 to pi over 4, pi over 4 to pi over 2, 3 pi over 4, and so on. So that thickness is the height of the cylinder. Okay, keep in mind if we drew the cylinder in 3 dimensions, we'd have some shape like this. We'd have a radius, and that dimension right there, which is our thickness that we're looking at, is the height. So with that, if we do our squaring here, we get 2 over 4, which would be a half. So ultimately we get pi squared over 8 for that one. A half times pi over 4 would be pi over 8, times another pi would be pi squared over 8. And then if we did the same thing with the next one, our next one is measured at sine of pi over 2 as our height is measured, so that would just be 1. And again, pi over 4 being the thickness. So this time we get pi squared over 4. And then third one, we get 3 pi over 4 squared. And not 3 pi over 4, the y value there would be radical 2 over 2 again. So the y value at 3 pi over 4 is this height right here. And so again, we'd get the same thing we got the first time, which is pi squared over 8. So ultimately we'd end up with, if we added these three together to get our total area, this would be 2 pi squared over 8 plus 1 would be 4 pi squared over 8. Oh, this is radical 2 over 2. We're putting 3 pi. We're putting 3 pi over 4 in here to get this value, which is radical 2 over 2, same as it was at pi over 4. So these two are the same. So ultimately we get 4 pi squared over 8, which would be pi squared over 2. And what does that equal approximately? I do pi squared divided by 2.
4.935.
Alright. And ultimately, again, this is just an estimate for what that volume would be, 4.935 square units, whatever the units may be here. They didn't give us units in this problem. And ultimately, they want us to use the integral command actually to find the actual area here. So keep in mind that with the formula that we're using, we can use that same formula in an integral here. If we go from 0 to pi, because we're going to sum up ultimately all the volumes instead of just these 3 volumes, we want to have an infinite amount of subintervals. Right, and let the, again, if we let the number of subintervals go to infinity here, okay, we're going to end up with a definite integral. Right, the equation that we're going to work with then is going to be this pi r squared h, and when it becomes an integral, that thickness is going to be infinitely thin, so that's why it changes from, instead of a change in x, which is our height, okay, which it's going to be delta x, or it's going to be delta x in the original, but when we write the integral it becomes dx, and then ultimately what defines my radius? The function itself defines the radius, doesn't it? So therefore we're going to have sine x in here. And what does that equal if we do that calculation with our integral command of the calculator? Yeah.
Why is there a page vector product?
Remember, the formula we're working from is pi r squared. These aren't rectangles, they're cylinders that we're creating here. So this is the formula that is our integrand. Okay. So again, pi r squared is this part, and then the height of each rectangle is going to be infinitely thin, so that becomes our dx. And again, everything is stemmed from the fact that instead of making rectangles, we're making cylinders, and the cylinders have this as their volume. Instead of having a rectangular area, we have a cylinder volume instead. So that becomes our integrand instead of a rectangle equation.
So our equation will always use pi r squared for any.
If we're making cylinders. Yep. So the height again is just determined by the sine. In the previous problem we did, it was determined by some circle function, right? So we had square root of 36 minus x squared in here, something like that. But in this case, it's just sine x. If we just had plain old sine x in here and nothing else, if it was just sine x dx, we get the area under the curve. True? But we don't want the area under the curve. We want the volume of that curve being rotated, which ultimately again becomes a 3-dimensional shape or cylinder instead of a rectangle. So exactly. So what are we at? 4 point. Again, same answer. Jeez. It's pretty accurate then, even with 3, isn't it? So keep in mind though that we got some that are underestimates, some that are overestimates. We got one that's a big underestimate here, but that ultimately that's areas getting accounted for by the other parts. All right. What else? Chapter review. And 11, we have a graph here, a velocity graph. It says that the body is moving along the s-axis during the time interval from 0 to 10. And part A says about how far did the body travel during those 10 seconds. So ultimately, if we have a velocity curve of any sort, and we know that the velocity in this case is measured in meters per second, time is measured in seconds, ultimately what are we going to get here for our area part? If we were to calculate the area under the curve, it would be meters per second times seconds, would give us total meters. So with that said, if the part A question then is, how far did this thing travel? Well, we'd need to find the area under that curve then, would we? So keeping in mind that there is no actual function here, we could ultimately consider those rectangles to be 1 square unit, or those squares to be 1 square unit apiece. Can we just count the squares in there and then just kind of estimate the halves and quarters and whatnot? That's all we really need to do here, just going to get an estimate of how much area is under that curve. Because we don't have there's no function we can integrate or nothing like that, so we basically just need to count. So if you look at your, count how many whole boxes there are, and then like I said, just estimate the halves, put those together, and you're going to just add those up. So if we have something like this, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, count all the whole ones. And then start going around the edges where the halves are and start kind of putting them together in your mind. And again, are we all going to get the same answer for this problem if we count how many boxes we estimate there to be? but we should all be within a reasonable amount of each other, right? I don't know what the answer is. I can't remember off the top of my head. But you got that? 26 and a half. So it should be somewhere in that neighborhood. Again, it's just your count. And then how about in part B, it says sketch a graph of S, which is the position function, okay, over this interval. And again, assuming that the S of 0 is 0. So keeping in mind, if we're going to draw an antiderivative graph, which is what we're doing here, antiderivative of the velocity is the position. So if we're going to try to draw a position graph here, we know it goes through 0, 0. We know it goes from 0 to 10. That's our time frame still for this one. And ultimately, we need to look at our velocity here. What's one thing that's always true about our velocity is always positive. True. So if our velocity is always positive, that means that what we draw here better be always increasing in some way. Okay. Keep in mind, though, that the velocity curve has a positive slope and then a negative slope. So remember that the velocity being the derivative, that means the second derivative is positive, then negative. True? So if the second derivative changes from positive to negative, then the function we draw should have an inflection point then, shouldn't it? True? Okay. Because our function should change from, in this area, concave up, to this area, concave down. But again, all the while, we're still increasing. So if I go from concave, I want it to be concave up first, right? So if I'm concave up, then, and it's concave up and increasing, I wouldn't have to have that type of shape. And then if it changes, still increasing but concave down, then couldn't it be something like that? Think about why, what's our velocity here? Let's just say, for argument's sake, the velocity looks like it's almost 5, right? Which isn't this the highest the velocity gets? And shouldn't that match up with where our slope is the biggest for this function? Remember, this function's slope gives us this function's y values. Okay. And ultimately, what is the velocity here? Almost what? Actually, it is 0 according to the graph there. So is it surprising here that it's flat down here? At time 0, the velocity is 0. We should have something flat here. And ultimately, at time 10, what's the velocity again? 0. So is it again surprising that we're at a slope of 0 here? So the slopes of this curve need to match up with the y values of this curve. This curve has a slope of 0 here, or this curve has a value of 0 here, a value of 0 here. So our curve that we draw, the antiderivative, should have a slope of 0 here and a slope of 0 here. Our curve is the biggest value here, so our slope should be the biggest here. And this is where our slope is the steepest, matching up with that same maximum point. Okay. So again, that's just a rough sketch of what that position function would look like for that particular curve. Questions on that one?
If you count the squares for the first one, is that just divide it by 2 or something?
The y values are halves. Okay, so actually those are only worth a half each. So yeah, that's why you could count them and then divide by 2, recognizing that. Yeah, the y values on the side are only going by a half each of those tick marks. What else? On 13, it says find the total area between the curve and the x-axis, and we're looking at the curve 4 minus x. So 1, 2, 3, 4, 1, 2, 3, 4. Our y value, 4 here, 0, 4 would be a point. Yeah, that's correct. And then 0, 4, or 4, 0 would be a point. So ultimately we have this linear function, and we're going to 6. 6 in there would give us negative 2. So bottom line here is we want to find the total area. So that means if we were to go from 0 to 6 of 4 minus x dx, would that be the right answer? No. No. Okay, so this is not what we want to do, because that will not give us the total area. It'll count the negative area as negative. We want both areas separately and make the negative area positive, and then add them together. So ultimately we need 2 integrals. We need to go from 0 to 4, because that's the positive part. And then from 4 to 6, 4 minus x dx. And ultimately we want the opposite of that one. And then ultimately we're going to add those 2 together. So if we find our antiderivatives here, we got 4x minus x squared over 2 from 0 to 4. And if we calculate, we're going to get 16 minus 8, so that'd be 8. And we don't need to worry about the 0 because the 0 will make both of those zeros. Keep in mind that if this is a 0 right here, okay, are all antiderivatives going to be 0 if I put a 0 in? Not necessarily. Okay. So it is in this case because they both have an x in them, so they're both going to be 0, but not always. So make sure you don't just see a 0 and blow it off. Okay. Depends on what the equation is. So that part being 8. And then if we do the same thing here for this part, we throw a 6 in there, we're going to get 24 minus 18. Should be 6. Minus 8. 4 in there will give us 8, so we get negative 2. And so ultimately the individual areas here would be 8 here, negative 2 here. And with that said, is the answer 6? No, because we're going to make the negative area positive, and we add it all together and we get our final answer of 10. Okay. Now, would there be another way we could have done that besides using antiderivatives? Yeah, they're both triangles, so couldn't we just find the area of the triangles and done it that way too? Questions on that one? So again, key information, if we're trying to find the area between the curve and the x-axis, we're asking for the actual area here. Okay? So we should not have any negative areas, even if they're below. Okay? We treat them as if they're not below. And remember, from the if we use the integral command, okay, what would we have done instead if we wanted to use the integral command? Say this was on the calculator portion of the AP test. Could we have done that in one sentence? So what would we have to do to this to adjust it so it would give us the actual total area? We do the absolute value. We'd take that negative part and put it up top. Okay. So if we did that, we would also get 10. So if we wanted to check our work, we could do that too. What else? 43, we got a marginal cost function. And again, the giveaway here is thinking about the units here. This function that we have, whatever it looks like, 2 over radical x, some kind of curve, whatever shape it is. The units here for the cost, they tell us here it's dollars per copy, and x is copies. So what's the area under the curve going to tell us? If I multiply dollars per copy times copies, that's going to give me total what? Total dollars. True? So with that said, it says that with this marginal cost function, this dx function, we have a rate function given. And we want to find it says the startup, including startup costs, it costs the printer $50 to print 25 copies of the newsletter. Okay. After which, the marginal cost is this, and the question is how much does it cost to do 200 or 2,500? Okay. So keep in mind that it's going to cost us, if we want to look at the total cost here, it's going to be $50 just to do the startup and make the first 25 copies. Okay. And ultimately, remember, what's going to give us the total cost for the 26 through 2,500? It's going to be the area under the curve, which ultimately is going to be represented with a what? An integral. So if we write the integral from 26 to 2,500 of our marginal cost function, okay, that right there would be an expression that would give us the total cost. Okay, why are we starting at 26? Because we already made the first 25. Sure. It says that after we've made these 25, the cost is this much, and so on. So bottom line is, whether by hand or by a calculator we get an answer for this, we can ultimately, this is the answer, we just need to calculate that integral. If we were to anti-differentiate here, I'd rewrite it as 2x to the negative 1/2. First thing I'd probably do is factor the 2 out of there, get the 2 out of there, so that's not even an issue anymore. Okay. So if I wrote it, I'd have 50 plus 2 times 26 to 2,500, 1 over x, radical x, that is, dx. So ultimately, if I have x to the negative 1/2, if I want to get the antiderivative, I'd go 1 up on the power divided by the new power. So it would be 2 radical x would be my antiderivative. You know what? Yeah, there's one adjustment I got to make on this. I'll do that in a minute, but still got a 2 out here. When we do our lower limit here, this actually even though in this particular context we're talking about copies of a newspaper here, It's still the right practice though, even though our domain should really be whole numbers in the scheme of things. Should be not to lose the 5 through 26 numbers, like 25 and a half, if you will. Okay. So really, we want to go start at 25, even though we, up through 25 is accounted for. We want to go count through 25 through 2500, and so we'll actually make that 25 instead of 26 at the bottom there. Okay. Okay. Yeah, we would lose some area under the curve, if you will, if we did that. Like I said, even though the domain here is really theoretically just whole numbers, okay, we don't want to lose that area that we would lose by doing 26 instead of 25. So with that, if we put our numbers in here, we get 2500. Square root of that is 50. So we'd have 100 in here, 200 in there, be 250. Actually, we don't want to add that yet. Use this whole thing first, sorry. So 50 plus, and then we do 250 would be the result from putting 2500 in there. 50 here, out of that, times 2 is 100, times 2 is 200. Right, and then a 25 in there would give us 5, so we'd have a 10 here, times 2 would be 20. And so ultimately we'd have 50 plus 230, give us 280. That would be our total cost.
Did you still add that 50? Shouldn't it be 200?
Oh, this is 20, right?
Yeah, but
230.
50, shouldn't that be 200? Because then it's 50 times 2, which is 100.
Remember, the 2 is part of this integral right here. Remember, it's 50 plus this integral.
Oh, okay.
So ultimately the 2 comes out in front of the integral right here. So it's 2 times what the integral equals, plus 50 on the end. Ultimately the 50 gets added after we do the integral part. So the 50 is not times 2.
Wait, but like, I mean, if we put
Yep.
the 2 back here,
Like the answer should be 200 from putting 500 in.
Oh, I see what you're doing. I got you. So it should be 230 total, not 280. So this should be 180 in here in the parentheses. I got you. Let's see if we set it, and then I still put it in there anyways. So ultimately, yeah, you got 200 from putting the 2500 in there. Cause you got 50 times 2 times 2, 200, and 20 for that, be 180. So total would be 50 plus 180, 230. Good. All right. So again, key element here is recognizing that marginal cost. If we have the marginal cost, the dollars per something, okay, that the area under that marginal cost curve is going to give us total dollars. Okay? So if we want to know the total cost for something, we're going to make an integral out of the marginal cost function, and that'll get us back to cost. What else?
45.
And 45, we got, it says here to solve. We got an integral expression 0 to x of t cubed minus 2t plus 3 dt. It tells us that equals 4. And ultimately we want to solve for x here. So we got a variable here that's in the upper limit of the integrand. Okay, keep in mind though that just think about what is this telling us. That ultimately this is expression for the area under this curve from 0 to something. True? And that area equals 4. Okay, so bottom line is, could we simplify this left-hand side? Could we find an antiderivative for that? So if we did, it'd be t to the 4th over 4 minus t squared plus 3t on 0 to x. Even though it's not a numerical upper limit, we can still find the antiderivative and plug it in, can't we? Because ultimately this left-hand side would now equal x to the 4th over 4 minus x to the 4th plus 3x. And then putting a 0 in there, we do a minus. The zeros in there would be 0. And so ultimately, wouldn't that be what our sentence looks like now? All right. So with that said, if we, whoops, that's squared, x squared. If we solve this, x to the 4th over 4 minus x squared plus 3x minus 4 equals 0. Coordinate function to solve. And I'd multiply by 4 here and get that 4 out of there and clear the fractions. Alright, and with that, we could see if there are any nice solutions to that by graphing. This would be, if we had to solve this coordinate equation, this would likely not be on the non-calculator part. So our equation to solve here is x to the 4th minus 4x squared plus 12x minus 16. And it looks like we do have two solutions here. Doesn't, however, look like they're very nice solutions. We use our, actually, instead of that, we'll do our zero command over here. And it looks like they're not very nice solutions. Keep in mind that of those two solutions that we have there, though, those are legitimate numbers, of course. I mean, we can use that for our x, true. And let's just say, for argument's sake, that that's the right answer there, that our x would be 2.1973682. So let's say that's our number. If we were to go ahead and do our integral command and do our x cubed minus 2x plus 3 comma x comma 0 comma 2.1973682. Something's not right. I got an antiderivative wrong somewhere, maybe. This is cubed, right? 2t plus 3. That's good. Got that correct. That's correct. That's correct. Four here. Four. Oh, that should be good.
Did you enter in the original equation?
Am I typing on here?
Yeah.
We're doing the integral from
Yeah.
x cubed minus 2t plus 3. Anybody seeing anything?
Nope.
I'll tell you what.
Go to the point you grabbed.
Yeah, that's a good pair.
Yes.
Ah, that's why. No, I want that though. So I want the zeros of that function. So let me try it again. So x to the fourth, right? Minus 4x squared
I can do what that is.
plus 12x,
Yeah.
and then minus 16,
Mm-hmm.
right?
Correct.
Ah, there we are.
That's different.
Yeah, that's definitely different. Okay, let's try that again. So we'll do our intersection command. Actually, not zero command. So 1.6305.207 would be our zero in question. Now, if we try that again, let's go back to our 1.60330. What is it? 5207. Ah, that looks better. All right. So again, this question with those kind of numbers would certainly not be on the non-calculator part. They wouldn't. But in theory, though, this kind of question could be on the non-calculator part because ultimately, if they had given us some antiderivative that was easily factorable or something that we could find an answer to, then that would be more than reasonable, wouldn't it? Okay. So key information again, though, is that we make sure from this expression, if this expression is true, all we're looking for is what x value here would give us the area to this be equal to 4. And the area of this we know can be found by taking the antiderivative, plugging in the x and the 0 and getting an expression. If we know that's equal to 4, then it's just an equation solving problem. Mike?
What about the other answer for x? Three.
If we put the other one in there, it's probably going to give us,
It's still
does it give you,
still around 4.
does it give positive 4 though?
Yeah.
Because we're going, trying to think of, because the function itself would be,
The other
actually the function itself would be negative, but if we're going backwards, that would make it back to positive. So yeah, we would want both of those, wouldn't we? So if you look at the, find the other, what is it, 3 point, negatives, 3 point something?
3.091.
9, look at if we were to look at the picture of the original function here, because again we want the area of this cubic function. So x cubed minus 2x plus 3. We look at the graph of the original here, and we go from 0 to 1.6 or whatever. There's our 4 there. If we went from 0 to negative 3 something, here's our 1, 2, 3. Ultimately, we'd have. Keep in mind, going backwards, this positive area would get counted as negative. But once we got past this point right here, which looks like it's 2, I guess, close to 2 at least. Yeah. So 1 point something. Again, going from 0 to this would calculate this area. And keeping in mind, calculating backwards, it would calculate this part as negative. True? But then once I got here, all the way out to 3 something out here, and all the way down, okay, that's going to calculate that all as positive. Because remember, going left would be the opposite of what normally is. And normally this would be positive, but going left it becomes negative. This would normally be negative under here if we were to draw this area. If I were to shade this part right here, if I could, that part would be normally negative because it's below the x-axis, but we're integrating left, so that would make it back to what? Positive. And ultimately, what's the difference between these two areas then? 4.
Why are we integrating that?
Because we're going, our original integral is from 0 to something. And if we go 0 to negative 3.019, which is that other 0 of the equation we solved, and the equation had 2 solutions. So if we check them both, they both work. But that's why they both work, because this is going in the negative direction. That's going to treat that as negative. It's going to treat this as positive, and ultimately there's
Cancel out.
4 more in this part than there is in this part. If we were to calculate from this point to 3.09, we'd get something that's 4 more than what we get if we did this one. So ultimately, 2 solutions, both should be checked, and they both work in this case, so they both do give us 4, so they would be both valid answers here for us. Okay. Good one. What else? On 54, we got an area function that is called g of x. And with the curve that we have here, we're going from 0, negative 3, 2, 2, and then we got a segment. So we got a semicircle and 2 segments, as it says, and our g function is defined by the area under this curve from 1 to x of f of t dt. So keeping in mind that this 1 is our starting point, everything is measured from 1 here in terms of the g function. So the integral, it's the area under the curve from 1 to x, if you will. And so in our first part here, we're asked to find g of 1. So g of 1, if we were to put a 1 into the g function, we'd have the area from 1 to 1, which we know is what? There is no area from 1 to 1, is there? So that would be 0. If we wanted g of 3, okay, ultimately g of 3 would be the area accumulated as we go from 1 to 3, which means it's ultimately the area of this triangle. So the area of the triangle will be 1/2 times 2 times 1. True? So the area would be 1. But since it's below the x-axis, it would be negative 1. And then if we do g of negative 1, going back here to negative 1, what shape would we be dealing with? Quarter circle. So ultimately it would be pi r squared. Our radius here would be 2. So it would be pi times 2 squared, so it would be 4 pi, but only a quarter of that, so ultimately it would be pi. However, if I just put pi here, that's not going to be right because I'm integrating to the left. I'm going from 1 to negative 1. True? If I go from 1 to negative 1, then my positive area then becomes what? Becomes negative. Okay? So my g of negative 1 value would be negative 1 because, again, I'm integrating from 1 to negative 1. So I'm integrating to the left, which makes anything opposite in sign of what it normally would be, according to our properties of or properties of integrals. All right. Questions so far on A, B, or C?
Wait, how did you
quarter circle. It's got a radius 2. Pi r squared is the area formula, so 4 pi, quarter of that would just be pi. But again, it's negative because we're going from right to left, if you will. Alright, how about part D? Let's check that out. It says find all the values on the open interval, values of x on the open interval, -3 to 4, at which g has a relative maximum. So keep in mind here that we're looking at an open interval. We can't consider the endpoint, so that means that our only possibilities are when the derivative equals 0, right, or when the derivative doesn't exist. And keep in mind the derivative of g, the function in question, is f of x. Okay? From the fundamental theorem, we know the derivative of g is f. We're looking at a picture of the derivative. True? So again, the issue is when does g have maximums or minimums? When the derivative equals 0, or when the derivative does not exist. So ultimately for part D then, what are our candidates? Can't use -3 because it said on the open interval -3. So it would be 1, 2, and 3. Why 2?
Because it's a corner.
And the derivative is a corner, but now we got to be careful here because ultimately, does the derivative not exist here? Remember, this is the derivative. Okay? The derivative of the derivative doesn't exist here, but does the derivative exist? The derivative is equal to -1 here, isn't it?
Is this a derivative?
This is the derivative.
Oh.
Remember, g prime is the area function, or g is the area function. What is g prime? It's f. Okay, this is a picture of f that we're looking at right here.
Yeah, it says.
Where does it say that? Do we just know that?
It says right above your ABC, it says let g equal the area under the curve from 1 to x of f of t dt. Okay. And how do we know this? Fundamental theorem. Derivative of g is the integrand evaluated at the upper limit. So what is g prime? It's f. Okay. And ultimately, again, we know that our g function is going to have a maximum or minimum when its derivative is either 0 or doesn't exist. Okay. This is the derivative. It's equal to 0, I agree, at 1 and 3, but does it not exist at 2? It's equal to -1, it exists. Okay. Now, is the derivative not exist here? The derivative of the derivative? Because remember, this is the derivative, right? Okay. So the derivative of the derivative doesn't exist, okay? But the derivative itself exists. In fact, it's -1. Okay. So 2 is not a candidate then because of that. So bottom line, which of these two candidates is the, they want to know which one is the maximum. Okay. Well, keep in mind, again, this is a picture of the derivative. At that point 1 where you mentioned, the derivative goes from positive to negative. So that's the maximum then, isn't it? And again, why? Because f, which is equal to g prime, changes from what? And be careful how we say this because we're saying that f changes from positive to negative. Okay? Which ultimately means the slope of g changes from positive to negative. Okay? Because f is the slope of g. Okay? Alright, so how about part E? It says in part E, write an equation for the line tangent to the graph of g at x equals -1. Well, ultimately, if we're going to write the equation for any line, we're going to write down the point slope form first. Okay. And let's see if we can come up with a solution here. We want it where x is equal to -1. Well, up here we figured out what g of -1 is. We have the point right here in front of us, don't we? So ultimately it'll be y plus pi, x plus 1. Now what about the slope? Okay. Remember the slope at -1, and remember, keep in mind that the slope of g is equal to f. So ultimately if I wanted g prime at -1, wouldn't that just be f at -1? So what is f of -1? It's 2. So there's your equation for the tangent line for the graph of g. Alright.
Wait, how'd you find the slope?
The slope of g is the same as the y values of f. So what is f of -1? It's 2. Alright, and f here says find the x-coordinate of each inflection point of the graph of g on the open interval. So again, now we're talking about the point that Justin mentioned. What are the candidates then here? Well, ultimately, again, the second derivative equaling 0 or not existing, that's going to be a possible inflection point for the graph of g. So remember, the second derivative is the derivative of our picture. Okay, so is there anywhere that the second derivative, okay, which means the derivative of this picture, is there anywhere that equals 0 or doesn't exist? Well, going from left to right, wouldn't the second derivative equal 0 right here? So that means negative 1's a candidate. Wouldn't the second derivative equal not exist right here? So those are our two candidates. True? So the question is, are either one of those or both, are they, or neither, are they inflection points? Well, again, keep in mind that what has to happen at an inflection point is that the second derivative has to change from negative to positive or positive to negative. So what's going on here at this point? Okay, the derivative of our derivative is positive here, and then it's negative here. Did it change? So we'll go yes on that one. So x equals 1 is because, again, f prime, the derivative of f, which we know f is the derivative of g already. So f prime, which is the same as g double prime, changes from positive to negative. What about at 2? At 2, what's the slope like on the left of 2? It's negative. And what's it on the right? It's positive. So we'd say yes to x equals 2 also because, again, the derivative of f, which we're looking at right here, which equals g double prime, okay, changes from what? Changes from negative to positive. Okay. So again, the slope of the graph that we're looking at indicates the second derivative of g because it is the derivative of the derivative. All right, and then finally, in part g, it asks us to find the range of g. So we're going to find the range of g. So ultimately, we have some values of g right here that we did above. We know that g of 1 is 0. We know that we get negative 1, negative pi. And I want you to think about this. If I were to if I go from 1 to negative 1 in our picture here, I accumulated negative pi, right? If I go further over here to this point, wouldn't I accumulate another quarter circle? So ultimately, what would g of negative 3 be? Wouldn't it be negative 2 pi? True? All right. So if g of negative 3 is negative 2 pi, and then what's going to happen here when I get to 1 to 1, I'm up to 0 finally, right? And then when I go to 3, I'm at what? I'm at negative 1. So ultimately, what's the lowest that I can possibly get in terms of y values here? Isn't it this one? Negative 2 pi. So ultimately, negative 2 pi is the lowest it gets. And how big does this thing get? Keep in mind, at this point we're at 0, right? And then what did we do? We accumulated negative area, so it went back down to the negatives again, right? And then for this little last part, from 3 to 4, okay, we accumulated some positive area, didn't we? But ultimately, if we're at 0 here, and at here we're at negative 1, is this going to be enough positive area to get us back up over 0? No, isn't this only a half right here? So we're at negative 1, and then if we add a half, we'd be at negative 1/2 at the final, at the 4 point here, wouldn't we? So ultimately, g of 4, even though it didn't ask us in this part, would be negative 1/2. So ultimately, how big does this function ever get? And the biggest value we get to is 0, isn't it? Okay. So therefore, that would be our range. Sorry. Ultimately, again, from here, we're at our g of 1 is 0 at this point. It's negative all the way up to here. Okay. It finally gets to 0 here. But then what do we do right when we get to 0? We start accumulating what? Negative area. So we go back down to negative 1, right? And then from 3 to 4, we accumulate positive area, but only what? Only a half. So we get from negative 1 back up to negative 1/2. But ultimately, how big does this ever get? The biggest value we ever achieve on this function is what? 0. Excellent question.
How does it even make it to 0?
What is the, remember it's defined as the integral from 1 to x. If I put a 1 in there, what do I get?
Oh,
I get 0. All right. What else? 56, we have similar to the one that we had about the lake in our section 5.5. We have town wants to drain and fill the small polluted swamp below. Average is 5 feet deep. And about how many cubic yards of dirt will it take to fill the area after the swamp is drained? So ultimately, the information they gave us, remember, is information enough to give us the surface area, if you will. And keep in mind, if we have the surface area, we treat this like a prism with a surface area of whatever, base area, if you will, and then times 5 is our depth is going to be 5 in this case. So ultimately, if we use our trapezoidal rule here, our spacing, remember, is the 20 feet they give us. So that means it's 20 over 2 would be our h over 2 part. And then our going from left to right, we'd have 146, and then 2 times 122. And this part gives us the estimate for the surface area. 2 times 54, 2 times 40, 2 times 30, and finally 13. So ultimately we have 10 times all that stuff. So we get what if we calculate that? But you have it handy on the paper.
So right.
Hmm.
That's right.
7030.
And
So keep in mind again that would be the surface area, if you will. That's an estimate for the surface area of this based on our trapezoidal approximation. Okay? And ultimately, if I want the area of the actual swamp in terms of adding that third dimension to it, then I would just go this times 5 and I get how much?
yeah, it's 80, 30. That's 80.
Oh, 80, 30. 80, 30 times 5 then would be,
40,150.
and it would be in what units?
Feet cubed.
Feet cubed.
That's a volume.
So again, the trapezoidal approximation just gives us the area of that surface. Okay? And multiplying it by 5, which is the average depth, gives us that third dimension, which gives us ultimately a volume instead of a surface area. So that would do it. Questions on that one? Others?
It says that you want to know how many cubic yards of dirt,
Oh, does it say cubic yards?
cubic feet.
Yeah, good question. I guess if we want to get the question right, we better read it carefully.
Why is this dirt?
They're filling it in.
Oh, this is the other one.
If we want to change feet cubes to yards cubed, remember the way that we do that here is we know that 1 yard is 1 yard is 3 feet, but we can't do 1 and 3 because we're not dealing with regular units. We're dealing with cubic units. So if we cube the units, what do we got to do to the factors? Cube them also. Not 3 over 9, but 1 over 27. Remember their volumes. All right. And so with that said, if we take 40,150 divided by 27, that should give us our yards cubed answer.
1,487.037.
So be that many yards cubed then. All right. Any other questions on that one? Okay. Tomorrow we'll go. We got 3 things. I'll answer questions from this if there are any more. Also from the any worksheet questions you have. We'll go over quizzes and then we'll start our grade book problems. Keep in mind the grade book problems are always going to be priority last because we'll get through the new material first and we'll get to those when we do. We'll just start knocking them off every time we get a chance. Okay? All right. That's it.
How long till we're on